This is part 2 of the PCB tutorial, and we'll be covering how to use the schematic editor, basic usage, and some design guidelines, and as well as the layout editor with basic usage and design guideline as well. And in the end, I'm gonna show you how to print your PCB if you want to print your PCB outside Micro Robotics. Just a review of what we have covered last time. PCB have multiple layers, and the most common layer is silk, solder mask, copper, and substrate. So the silk is the marking layer on top of the PCB that you can put graphics and text to indicate which part is what, and what's the input and what's the output. Solder mask is the part that restricts the flow of solder, so allows the solder to flow only to one direction, so or only one single spot without them like spatter everywhere. So when the temperature is high, the solder will act like a liquid and it will flow everywhere without the solder mask. The copper layer is the layer that actually conducts electricity and allow you to connect things together. And the substrate layer is the layer in between that separates the two copper layers. And for entities, we have pad, pour, and plane, and trace, and via. So in this small picture, you can see all of them. So there is a pad like this. So these are the things that you solder component onto. Pour and plane are region of the copper that is defined by a boundary, and it will try to follow the boundary and without touching other components. Trace are the wires that you use to connect to each individual component. As you can see here, there's a trace connecting here, and it gets split into different places. And via is the last thing. So via are small holes that allow you to pass signal from one layer to the other. So these are the entities that we're going to be using. So let's get started. So first thing first, we're going to launch a schematic capture. And for this exercise, I'm gonna do something relatively simple, and I will be using the depth sensor we used last time to make a schematic for it. So the first thing you start a schematic is to copy the schematic template from electrical ripple and to somewhere else, and open that copy. So this gives you a nice border for your schematic and allow you to put some information onto it. So for example, this will be part 2, and the project will be just gonna put something.
Where do you get that from?
Electrical ripple. So if you have access to Micro Robotic Electrical, you'll be on the schematic template on top, the first thing, on the root, GitHub, yeah. And then so we're gonna find the depth sensor, which is MS5055805. So that is the first thing. We're gonna put this onto the schematic. And here is our depth sensor, and the data sheet is attached to it as well. So I'm just gonna load the data sheet. 580. No,
803.
Oh, there's 3. Wait, that's something I need to be fixed. So this is the data sheet for the depth sensor, and we're gonna use it. So for usually what you have to do for a datasheet is go to their typical application and apply that with some modification to better suit your need. So I will try to find if there is one typical application in this datasheet. So here, the I2C protocol, this is what we're going to use, and we're going to use this as an example. So in terms of functionalities, we want to use a 5-volt signal and a ground signal, as well as SDL and SDA. So to do that, we need a connector with 4 pins. So with that, I'm just go to component, con header, to add a 4-pin connector from the con header. And as I showed before, to place component, you need to find it in the library, and then you click the component itself from the library. Then you can and then you click on the board. You'll display the component. So is everyone following? Everything good? Okay, and for this IC, that it requires a voltage of 3.3 volt, but in our made up scenario, we can only generate 5 volt, so we're gonna need a voltage regulator as well. So for that, I am gonna use TLV 702. So this is a small regulator that regulates the voltage from 5 volt to 3.3 volt. And if you want to add a library that does not exist, or for example, if you want to add the library you have already on GitHub, you go to you click on this area of the screen. So there's an arrow over here, and go to library setup. So for user component, you can add a library from the Amiga Robotic repository, which is the components folder under electrical. And for the pattern as well, so you add your component library from electrical. And if you have your own library, you can add them as well using this, or it's simply just add to the library's symbol file. So let's place our components. So what we need as a component are that there are input capacitor, output capacitors of the linear regulator. So I'm just open up here. This is a typical application. So the input with a capacitor, the output with a capacitor, and the enable is strapped to it's a high or low depending the state of the regulator. So to do that, first thing first, we're gonna get some capacitors. So we can go to decrease surface mount and use 0603 capacitor. So that's the most standard size we're going to use. If you could not find a capacitor of the capacity that you want, or the voltage reading what you want, then you might use a different capacitor. That will be depending on your design. You can rotate a symbol by simply pressing space. That will rotate the symbol by 90 degrees, and we're going to do that. And another thing I would like to show you how to do is using netports. So there is a library called netport that allow you to connect things with a label. So we're going to use a 5 volt symbol here and connect the first pin to 5 volt. And we're going to use the ground symbol here to connect the last pin. To connect the last pin with ground. Note that when you do this, if I use the same symbol for something else, it will connect them together as well. So if I use 5 to use VIN and connect it, and you can see that when I highlight this 5, the other 5 will be highlighted as well. gonna drag this down a little bit. More room. And I'm going to connect the capacitor to the input of the 5-volt line, and copy paste this ground to the bottom of the capacitor, as well as connect the ground here to that capacitor. And then the enable line will be connected directly to VIN to always enable this voltage regulator. And on the output, I'm going to put another capacitor to connect them, and the ground as well together. And last thing, I'll label the other side as 3.3 volt. Now, although these connector, there's a net port to display what the net is. Still the net is will be unnamed by itself. So what you can do is you can double click on the net to give it a name. So right now this one will be 5 volt. I'm gonna just label this 5V0 and this 3V3. So this allow you, when you're doing the layout, you'll be very clear what this net is, and help you route stuff easier. And as well as I'm going to change the ground net to ground. And that concludes the part that we need to do for the voltage regulator. And then we will connect the depth sensor with the voltage we just generated, at 3.3 volt to VDD, and we're going to connect SDA to pin 2 of the connector, and SDA to pin 3 of the connector. And same thing here, we're going to copy the ground symbol and add a ground to the chip. And since we're going to use the chip in I2C mode, we can just go check how to select this to I2C. So we need to connect the PS pin to VCC, VDD, or rather just voltage high to select it to be the I2C mode, and we connect the CSB pin to one of the voltage, ground, or VDD to select the address of this chip. So with that said, we're gonna put another 3.3 volt symbol to connect the PS. The CS will be connected to PS, so to fix one of the address. Or what we can actually do is to use a jumper component. So if I can find it, user component. Solder jumper. Yeah, so we're gonna use a 2-pin solder jumper to be able to select to one of the configuration. DipTrace surface mount resistor. One thing to note is that if ever you see a pin with a square on top of it, meaning that it's not connected. Although it might seem that it's connected to something. For example, if I place it here, it might seem that this resistor is connected to this wire, but in reality they're not connected. They're not registered as the same net by the DipTrace. So that you have to make sure, if you actually want to do this, you have to make sure that this has to be connected to that. Alright, so now we're gonna need the pull-up resistor of the I2C bus and depicted in this part of the typical application. And just gonna rotate this to up position and copy paste it. And I will be pulling them up to 3.3 volts, so just copy the 3.3 volt symbol and connect it to both of them. Alright, the next step we're going to do is going to put all the value for the resistor and the capacitors. To do that, just double click on the capacitor resistor and just put a value. So this will be 10K, and this will be the 10K as well, and this will be 10K as well. So there are pull-up resistors, and the capacitance I'll be putting 1 microfarad here. Micro and 1 micro, and for the VDD line of the depth sensor, I'm going to put a bypass capacitor of 100 nanofarad. Depicted here. So I'm just gonna get another 30-degree surface mount capacitor like that, and just connect it here, bubble up a little bit, and put a ground to it. And connect them all. So after we finish this, so this is the backbone of our schematic, and it's a relatively simple one. And after finish it, we can use verification to do an electrical rule check to make sure everything is good, and to do check hierarchy but we don't have any hierarchy blocks, so it will be good as well. But if we have a resistor, for example, putting on top of a line but without connecting it, I believe this will warn us. And here you see here that although it's on top of the line, it's not connected, so it will warn us with pin no connection. Alright, so this is everything we need for our schematic, and there are some simple guidelines we want you to follow. So always use the default 0.5 grid, and keep 2 parallel wire 0.1 inch apart for readabilities. Minimize the number of corners that you use for your design, and try to have a T intersection instead of X intersection, because in the X intersection it will be very hard for you to figure out which wire is coming to what. Yes?
So you're always using the empirical system?
Yes, in the schematic you are using the empirical system, because the schematic has no bearing with the physical dimension of the board in any way.
So for other like let's say the PCB layout, I can use it to be
Depending on the component that you use, you can use as empirical or metric. But I think empirical is still preferred in PCB manufacture. So, but it has no difference in terms of how to generate just a unit. So preferably the input will be on your left and your output will be on your right. Higher voltage on the top, and the lower and the ground and lower voltage at the bottom. you should and should rename your net to give it a more descriptive description. For example, I'll rename this net to SDA and the other net to be SCL. And then separate different part by function using net ports to make them more clear. And use so at the end of your schematic, you're gonna have to include a text file, a README file when you upload it to the GitHub to explain the functionality and how you implement it. All right, so we're gonna save this. So we're gonna save this as because we are still using the schematic template name. So I'm gonna save this as and now we can close this. So there's nothing to be done with it. And then we're gonna open the layout editor, PCB layout. Now we can use the layout editor to open schematic of this. The layout editor is able to open both schematic files and as well as layout file, so that when you start laying out something, you will start with a schematic file, but after you save it, you can use you should use your layout file that you saved. So just double click it, and we're going to use the schematic rules. So just click OK. So here we see all the components that was selected on that was put in onto a schematic. Most of them are in the relative position where the schematic is put, but it has no real meaning. So the first thing we do is we go to placement, arrange component to make them closer, such that we can manage them easier. And I prefer to not have the component marking on top of each of the component, so we can go to component marking main to display none to remove all the marking of the different part. And this is our component that we need to do to route the PCB, and we're gonna start routing the PCB, I guess. So you can drag a component very easily just to place them, and you can rotate the component by itself to put them into different orientation. Usually there's 2 layers of PCB, so you can press B to go to the bottom layer and T to go to the top layer. And to put the component onto a different layer, you right click on it and you click change side, so that will put into the bottom layer of the PCB. And with that said, and we're going to change this to the top as back. And route the net. So relatively, the first thing we want to do is to put all the components relative to where they are, where we want it. So I'm going to rotate this connector. Although it says the board edge is here, I'm going to use that side as a board edge, and this will ease up our connection a little bit. So I'm going to put a voltage regulator on top with its capacitor. So 1 microfarad, it's over here. Put it on here, and the other side will be the output will be connected to another capacitor. So 1 microfarad here. One thing I would like you to do is select all your component, and you snap to grid by the origin instead by path, so that will make your schematic look that will make aligning all your component much easier for you to do. And so in this case, we can start using a smaller grid to make all your component fit better. So we're gonna do that. Capacitor here, like that, and what we're gonna do is we're gonna hand route our stuff. So from VCC to the input capacitor to the voltage regulator, and then we're gonna put the enable pin of the voltage regulator by connecting it like that, and then the ground will be connected, and we're gonna use a via. So click a wire anywhere and press the bottom and or top layer to make a via on the other side of the layer, and we're gonna press enter to terminate this wire, and then you'll have a small tail over here, but that will be okay once we pour the ground layer onto the bottom layer. Yes.
Should we try and limit the amount of wires we have on board?
Yes, you should try to limit the amount of wire on board. But for ground plane, it's better for you to use a wire because use a via because that's the easiest way for you to connect to the ground,
Okay.
and that has the lowest resistance compared with the other method. All right, so our ground to here. So this is our jumper cable, and we're gonna try to place this here. So we can highlight our output. This net is where we're gonna put our VCC. So I will be connecting our VCC with like that, and SDL is this pin. SDA is this pin, and SCK is this pin. So for the two resistors, I will be connecting SDL and SDA. I'm gonna place it closer to where it goes to, in between. And this is the ground, and I will have to flip those resistors location. So I'll move things around a little bit. So what we're going to do is we're going to connect SDCL and SDA. And then we're going to have to connect the ground pin to ground. We're going to do it with a wire, so like that. And this is our address select, and we're going to select the address based on that. But first thing first, we're going to move our capacitor up a little bit and put our bypass capacitor next to the VCC of the chip. So this is a resistor, and this is our bypass capacitor. And as you can see that it won't fit well, so I'm going to reduce the grid by a little bit as well, and try to connect it like such. So for bypass capacitor, it will be better for you to go through the capacitor before you go to the pin. So I'm going to try to do that for the capacitor and connect it like that. And we're going to connect this to the ground by using ground via again. just go in here like that. And as you can see, this is too close together. I'm gonna move this down by a bit. Move it like that. And because the next thing we need to do is connect this to ground, so I'm just gonna connect over here and put the ground pin like that. And we need to put the resistor for our for our address select from here. So our VCC to here. And this pin goes to our address select pin, and the other one goes to ground. The last thing I want to do is connect it through here, and I believe that this is all the connection that we need to make, and I'm going to adjust the connector that we need to be connecting a little bit. And one last thing we need to do is we need to connect the pull-up resistor with the VCC of the net. So we're going to use a longer bias to do that. So what we're going to do is we're going to start here and immediately put a via here and trace this back across our schematic and go back to here and go to the top. And then connect them all. And last thing we need, one more thing we need to do is to pour a ground pulling at the bottom of our component. To do that, we just gonna select the port tool. And select the edge of the other contour of the port. So I'm gonna go to one's level higher. So that. And so we're gonna use a square port, and we're gonna, after we put all the vertices of the port, we press enter, and then we check the connectivity to be ground, to connect to ground. So ground, and immediately all the ground pin will be connected to this port. So finally, we need to add a board edge for the PCB to generate what's the actual border of the PCB. So we're going to do that by using the place board edge connect tool. So by clicking the same thing for ground port, we're going to put a ground edge and press enter. We're done, and we're going to adjust it as such. And one thing we need to always do is to label the pin and the connection that we're using. So for that, we're gonna use the label tool and use the top silk to label our thing. So we're gonna put for this address select, we're going to use this ADDR for naming that this is the address select, and we're going to change the font size by go to font, and I think for as a good size, 4 with 80% is a good size for you to put on your schematic. Of course, I can move this a little bit to make room for this better. go smaller to place it nicely. And then we're gonna do the same thing for the bottom layer to label all these four connections. So next we select bottom silk and print a VCC because so they are inverted because the bottom layer, although we see it on it's the top projection of the bottom layer, so the actual bottom layer will be a flip of what you see at here. So I'm going to change the same thing for this. So the font will be 4 with 80% text width, and place it as bold. And place next to the VCC pin, like that. And I'm going to copy paste it. So it's kind of weird how they change text. So you had to click the VCC label, and then you can change the text for it. So this pin will be SDL, SDA, and this is our SDA pin, and SCL. And ground. So one thing to be careful is that VIA will interfere with your text label, because because VIA is a drill hole and the text cannot be placed on top of it. So we're gonna move our VIA a little bit to fit it better to our label. So I'm gonna move this a tiny bit up. Maybe it says finer bit. And this one a little bit down, and adjust those resistors accordingly. Now that I move the vias, you can see the ground port is no longer following the contour of the trace. So what I'm gonna do is I'm gonna right click on the ground port and click update, and then this will be updating the ground port and allow everything to be good again, I guess. So the last thing we need to do is a few things we need to do is we're gonna do a design rule check to make sure that everything follows the manufacturer specification that allows us to do. So we're gonna do that, and we see that we run into some problem. So the gap of our trace here is too big, and the gap here is not enough for our design rule, and as well as here and here as well. So the two thing up here can be fixed by changing the via style. So I'm gonna right click on the via, go to via property. I believe the smallest via we can do with Electro, which is the manufacturer we make our PCB, is with the outer diameter of 0.025 inches and the whole diameter of 13 inches. So just click that, and this will be much smaller via. So this will be fix our two of the problems. And for there is a design rule depicting what's the distance between the pad and the outline of the board, so we can change that to a different value. So by clicking this button, so design rule, and we can change what's the rule that that design rule check uses. So I'm going to change it to 10 for the spacing between the board edge to all the components. That, and let's verify again, so there's no more error that I can see. and we can do check net connectivity. So this will check if there are any broken net or anything that's not connected, anything that's supposed to be connected on schematic but is not connected on the actual layout. So by clicking OK, we can check. Yeah, so there's no error be found. But if I delete one of the trace, for example here, um, and try to do that again, you see that VCC is 2.3 volt is broken, 5 volt is broken, and the ground is broken. All those pins are, so that's one way for you to make sure that your schematic is actually exactly the same as your layout. And another verification is compare your schematic with your layout. So we can click on compare to schematic to compare with our layout. So click on that, and there's no difference between our schematic and layout, so it passed this test. But to demonstrate that, I'm going to go back to our schematic. Sorry. So in this case, I'm going to delete the solder jumper and just fix the address of the pin by pulling it directly to the VCC, and save this. Now if we go back to schematic and try to verify that with compare with schematic, we will receive an error, so that there are unknown component onto schematic, and there are unknown component for the R1 because we removed those two components, and the net of the net depicted in the schematic is different than the net show in the layout. So to fix that, we're gonna go to File, Renew Design from Schematic, and click by component. So with that, we select the schematic we just updated, and click Open. So this will remove the component that was added by the. This will remove the component that was removed from the schematic, and then we can continue to fix our schematic. And sorry.
Oh well, do you happen to have a VGA on any of your computers?
Yeah, I do, but I tried. It doesn't help.
Because if you do the VGA one, it does work. Where's the other one?
So we're going to try to connect this pin with that again.
That works. Because if you use,
And
if you use both of
I
these,
tried 2 times.
let's try one more time. Because this worked last time I was down here.
Will it work in my phone? Just
No, because you have to have it on the VGA mode.
okay.
Well, actually, we could try that first.
No, I tried it in my laptop 2 times today.
With this cord as well.
With this too, yeah. This.
And then it was on VGA over
And
there.
then first after I put this in, that's all this.
But we'll try one. We'll try one. If that doesn't work,
Okay.
I'll do that.
Makes sense. Makes sense.
No, I'm gonna do it. I'm just helping them.
sorry, we have a meeting here. Can you?
Oh, I'm sorry.
I thought you were part of the group.
No, we're not. So that is the last step of the PCB. This is the last thing. This is the last step of the design of this board. Now we can 3D preview it by click on the preview and 3D virtualization, and so just ignore all the errors. So we don't have any of the 3D model attached to. I don't have any 3D model attached to my installation of the DipTrace, so I'm just gonna click OK. That will show us how the board looks like in 3D space. So there's that. We can close it. Last step we do is to export this PCB into a design file that can be printed by Electro by click on export, and the file that they use is Gerber, so I'm going to click on Gerber, and we're gonna export top mask, top silk, top mask, top bottom silk mask, top bottom silk. So it will be 6 layer that will be exporting, I believe. Yeah, so these are the 6 layer that we're gonna export, and we're gonna click on files to select the file name for each one of them. So so the naming convention of Electro can be found on Electro's net website. So wait, where did it go to? Yeah. So the top layer will be GTL with the name of the PCB. So I'm gonna follow that convention. So it will be and GTL, and this will be exported, and just gonna copy this. So this is not the actual top layer. So so top layer is top, bottom layer is G bottom layer, and you get the idea. So I'm just disable exporting for the rest of the layers, and so right now we're just gonna generate those 2 layers, but you need the ASICs to ship it to Electro, and yeah. So click on export L, and so it will be saved. It will ask you to save it will ask the location to save them. I'm just save on my desktop. So all the layers that were selected as yes will be exported this way. And after everything is done, you also need to generate a drill file. So by going to export and NC drill. So and then you're gonna just export all, and so it asks you if several tool not satisfied. You're just gonna auto select them. So just click yes, and drill file is naming convention is PCB name.txt. So you can just rename that afterwards. It will be okay. So I'm just going to save it for now and close it. So you have generated everything you needed to print the PCB, and if for robotic, you can pack this as a zip file, and then it will be shipped to Electro. And if you would like to print your own PCB, there are multiple manufacturers that can do that. For example, there are Oshpark, which print a purple PCB. So you can print the PCB over here, and you can also go to Electro, which is a company that we have a sponsorship relationship with them, and they are 50% off for our PCB. But I don't know if as a as a student you can get access to that PCB discount or not. So let me just check if there anything I would like to cover I have not covered. Place the label, placing the label, board outline, checking the board, design rule, and yeah. So some of the design rules that you need to follow is that do not not use a 90-degree angle bend. For example, this trace, you could do that, but try to use a 40 to 45-degree angles to make the signal flow through better. Place a bypass capacitor as close as possible to the component that it goes to, and allow them to allow them to reduce the noise get induced to the pin. And if the bypass capacitor is used to reduce noise of one pin, you want to make sure that the signal coming through is passing through the capacitor before getting through the pin. So for example, this is so the VCC is coming from here, it go to the capacitor pad and then go to the pin. And what you also can do is to connect it directly here, and the capacitor will be outside the pin, and this is less recommended. Use the ground plane. So use of ground plane will help with your noise immunity and allows the PCB to be more EMI resilient. And try to not have a loop in your ground, such that, for example, try to not have a trace in between your ground plane like this. I'm going to demonstrate what I mean by that. So right now, it's less a loop. So I'm going to move it here. So now your ground plane have a loop that around this trace, and if this hole get bigger, you'll be more susceptible to noise, and make your ground plane very noisy, and that will sometimes induce really weird errors into your circuit that you will be very hard to actually debug. Always label your LED's indicator and component that takes user input. For example, button, switch, slider, connectors, and all those components. Always label them to label what exactly their functionality is. And do not use. So DipTrace comes with the auto router functionality. Do not use it. It's really bad, and it will not make a good PCB. Last thing is do not delete traces. So use unroute trace instead of delete, because when you delete the trace, it will delete the net as well, such that this will no longer be recognized as connected to that, and this will make your schematic inconsistent with your. This will make your layout inconsistent with your schematic, and will make them not work because you're missing a net that's supposed to be connected. So for that, what you can do is use unroute trace, unroute segment, unroute trace, or unroute net to try to remove one of the wire that you have already placed. There is an unofficial DipTrace tutorial. So in that you can find about everything you need to know how to use DipTrace. And in the Google Drive, there's also a PCB design guideline in terms of how to properly do a better layout, and it has more in-depth rule that you should follow. And I also included highlighted portion of each individual part of it, such that you can focus on to the more important part of the layout guideline. So in practice, PCB layout is intuition. It's a skill of intuition. So you have to build it up by practice and by doing it a lot. So by doing it through a lot of iteration as well. So I usually routed my board twice before I send it out to be printed, such that the first time I just experimented with all sort of configuration, and the second time I'll have a better idea of where everything will be placed. And yeah, so this concludes the tutorial for layout. Do you have any question? No? Okay. All right.